All right, welcome back. So the last video was about the Word2Vec model, how it works in general, especially we're taking a look at the continuous bag of words algorithm and how it trains the embeddings of the words. And in this video, let's take a look where actually it comes from that the word is learning about the similarity. It kind of, where does it come from that it is able to generate similar numerical representations for words that have a similar meaning, and what does that actually mean here when we talk about a similar meaning. Okay, so let's take a look here. So where have we been, especially when we were thinking about the continuous bag of word algorithm? What we always have is we have two different sets of vectors. The first one is what I call the feature vectors, and the second one is what I would call the target vectors. So in that example here, we had kind of 14 unique terms, and counting at 0, and every term has a unique ID. So for instance, I is ID 0, so that is why it is here at the first position if we start counting in a Pythonic way. And that is if we use I as a feature word. And here that would be the representation if you use it as a target word. So that means when we want to calculate how large is the probability for observing the word I when we observe a certain feature information. And what does this have to do with the similarity learning? Okay, so I think this example is quite nice. So let's talk about those two sentences here. So we have I love vanilla ice cream and I love strawberry ice cream. And especially if you use a window size of 2 and we go to the words in the middle, you have vanilla and strawberry as words we would like to predict successfully. If we have see or if we have if the presented information is that I love and ice cream are the words surrounding these words. And when we have a trained Word2Vec model, and if we have trained it, or if we would like to take a look at the information as you would do it for the continuous bag of word algorithm, what we would collect is the vectors for I, love, ice, and cream, and aggregate them, usually by averaging them or by summing them up. And that is what will be what I call here the feature vector. And you can see this here. So it is with a 3-dimensional embedding, so 3 numbers, minus 2 point something, plus 0.97, minus 2 point something. And now what's the goal of a trained or a successfully trained model is that if we take a look now at the target vectors of the actual words of vanilla and strawberry and calculate the dot product of the feature information and the corresponding target vector, it's supposed to be a large positive number because later when such a number is transformed to probabilities, it's also going to be a large positive probabilities. And the dot product of two vectors is the element-wise multiplication and then just summing them up. And if you think about it like this, and if you just take a look at the first of the feature vector, how could you create something like this? So you want to have in both cases, so if that's just the corpus, I would say the probability when you observe I love ice cream is 50% in the best, and for a perfectly trained model, right? So because in 50, in half of the chance, or in 1 out of 2 times, you're going to observe vanilla, and 1 out of 2 times you're going to observe strawberry, and no other words you ever observe when you get this kind of information here. And so you want to have positive real value numbers, and they should be should result in a similar value, no matter if you use vanilla or strawberry. So if I want to have a positive number, when I have this vector given and I want to create another vector, I would say I would start like this. Okay, so here I would definitely give a vector which is also having here a negative, here a positive, and here a negative number. Because if we then build the dot product, it is minus something times minus something, which is positive, plus a positive number times a positive number, plus again minus something times minus something, which is a positive number. So if my vanilla vector or my strawberry vector all have negative, positive, negative, I'm quite certain, or I can be sure that both dot products are resulting in positive numbers, and I need a positive number for having a higher probability here, especially and they should be should equal also to a similar value. And here that is exactly what is happening. So these are the vectors of the trained model. So you can see it's minus, positive, and negative, and here negative, positive, negative. And also you also can see that the if you calculate the dot product here, it is almost identical. Here, just starting at these values, which is exactly what we need, because if we would transform this now, and I'm not doing this here because this includes all the other vectors again, and building the scores here, but if you would transform these numbers and all the other words have scores which are below this number here, those will be the two most likely words given the feature information I love and ice cream. And as they have similar scores, they will get equal probabilities, more or less. And this is exactly what fits to what we observe in reality, because we observe in reality that it's kind of equally likely to observe vanilla or ice cream once we are presented with I love and ice cream. Equally likely probabilities for vanilla and strawberry once we observe I love and ice cream. And usually, I mean, that's what I'm not showing here, but I hope you believe it. The scores for all the other words are lower here, and that's basically it. I mean, I can check out if we can quickly do this. So if we have the let's skip this. I think that would end up in a not so nice thing. You take a look at me figuring out how to multiply this quickly here. So nevertheless, now again, for a deeper understanding, so this is how it's supposed to be, and this is only possible if they have the same signs here, right? Especially the vanilla and the strawberry vector. Now, this is only possible if they have the same signs at the same positions, and also to end up with similar scores, they kind of need to have similar values in absolute terms here at each of these positions. And if this is the case, then those vectors are similar. So that means the similarity measure between those two vectors is going to be high. And if that's the case, then we know that the meaning of the words is high. That the meaning of the words is very similar. So that means the similarity here strongly also depends on the corpus. And here, if the corpus is about eating ice cream, similarity especially means similar with respect to what it is used here to describe something. Here it is the taste of ice cream. But the similarity, again, it comes from, I would say, that vanilla and strawberry are trained to be similar to each other without, in that extreme example, seeing each other together for, they would never, the words or the terms vanilla and strawberry are never used within one example here during training. However, still the model learns to relate them to each other. And how or why does it learn it? Because the words surrounding these words are the same. And by presenting the model sentences or window slides like this, if you want to like this in an indirect way, vanilla and strawberry learn that they are similar to each other. Okay, I hope this kind of makes sense. This is already quite detailed, to be honest. So if you're struggling with the general idea how you transform these vectors into numbers and create probabilities, then I think maybe go back or take a look at YouTube or Google if someone is better in explaining the principles here. But to me, I think this is a very important thing to evaluate for yourself if you already have a profound understanding. Because I think if you can follow this idea of if you kind of get this, then you really got the idea of the model and how it's trained, and especially what it means that similar meaning here is given. Okay. All right. The skip gram algorithm. Okay, sorry, this is too. Let's quickly go here to a light mode. So in this video, and especially in the last video, I think I in a detailed way explained the continuous bag of word approach. So I'm not planning to do the same thing for the skipgram model here. Skipgram, as you can see, is a big difference, but still it is what they have in common is it is about predicting words out of like the window of different documents. But while we are using all the words surrounding a certain word to try to predict the word in the middle, skipgram does exactly the inverse thing. So it uses the center word and then makes predictions for the words surrounding it. So if you take a look here, for instance, like I love vanilla, for instance, I think here then we have starting from vanilla, you can already create 2 examples. Okay, so vanilla and I and vanilla and love, and depending on the window size, even more, right? So I think here you really have naturally, I don't know if that's actually true, but more training examples created. But as I said, yeah, the idea is inversed here. Nevertheless, also again, you would have 2 sets of vectors. In that case, the words for the center word vectors are the feature vectors, and then for the words in the window surrounding the center word are the target vectors. But still, again, you're going to create examples, you're going to hand them over to the model, you use the vectors to calculate probabilities, and you manipulate the word embeddings in a way such that the probabilities for the words that we actually observe, given some information in terms of what is the center word, are going to be increased and by changing the numeric representation of the words here. All right. Some practical considerations. So originally, but also this is something that I think others can explain better, and it's not like in a broader picture, it's not super important because this course is more about introducing the idea of word embeddings here and not all details about the Word2Vec model. Like what we basically have, no matter if you have a continuous bag of words or a skipgram approach here, is kind of a multi-class classification prediction out of a neural network. In a very special case, because the great advantage is here that the training examples can be just extracted from the text itself and do not need to be labeled. And also the architecture of the neural network is obviously a little bit different from what we would know as a common forward neural network. Nevertheless, it is a multi-class classification problem. And that means the output for the prediction or the dimensionality for each prediction must be equal to the number of terms in the dictionary. So that means if we have a large corpus where overall, let's say 20,000 unique terms occur, then the probability prediction must be equal to 20,000, because given some information, what is the probability that we observe any of the potential words that may be in our dictionary? And yeah, this is obviously just without technical explanations a lot. So what is done here in reality are some alterations. Instead of exactly doing like this, there are things such as negative sampling or the hierarchical softmax approach. So if you're interested in learning about them, those are now the things you need to Google for and take a look. And then besides that, what is the common embedding size? In my opinion, it's something between 100 and 300, but as I said, this is kind of what you would decide if you would train the model. And always these things are kind of also a little bit of hands-on approach. So you're likely going to train the model with different dimensionalities and then figure out for yourself what works best here. Common window sizes are something between 5 and 10, maybe 5 and 15, kind of also depends on the nature of your documents. And for instance, some other aspects, so we've been talking about stop words or lemmatization or stemming to reduce the overall dimensionality of representation of documents when we use frequency-based approaches. Here, for instance, it is very useful in the more professional libraries such as GenSim, which we are likely going to talk about in the next video when I show you a quick demonstration how you could estimate your own Word2Vec model. And So what they do is they do some sort of also negative sampling. I think also this goes back to another paper by the original authors where they also kind of suggested to do this because it improves the training. And here you can, during training, kind of not sorry, no, it was negative sampling. It's mean what you basically do is when you create the examples for training the model, you use examples with words that do occur with large frequencies. You lose them a little bit, use them, I would say to a little bit less in reality when you train those models, such that your model is not dominated by very frequent terms, because those are usually also the terms that are not so meaningful to differentiate between the meaning and of certain text slides or the window slides. But those are like the technical aspects. And first of all, I am not 100% certain about them by myself. This is a very detailed thing. And as I said, it's more about introducing the idea of word embeddings. So if you're interested, as I said, the Jensen package in Python is really a good starting point to read about these aspects. And if you really want to dig deep here, I'm kind of guessing you're already familiar with Python and other programming languages. And then it would be a very good idea, for instance, to take a look at the GitHub of the Jensen package and explore the code for yourself, because there's a lot to learn here, I would say. But to me, it's, to be honest, most often also about the applications here. And here, let's just maybe talk like 5 minutes or something about what are like the common usages. And so obviously what you can do now is you can, and this is a very, in my opinion, spectacular thing, you can just calculate with words, right? Because they are vectors, and now you can choose regular vector calculus to regular calculus to handle words. So you can create things such as the average vector of words, and if the words, for instance, are similar to each other, then maybe you can create a vector that more or less describing a topic that is described by words, stuff like that. And also something which is where you can see this, and which is quite impressive. You can check out for the similarity of words. If you bring the embedding size down, you can visualize the words, and you also can create meaningful numerical representations of documents by averaging or by summing, for instance, the word vectors in a certain document. So this is what I have in here. If you would like to play around with that for yourself, I mean, now we're using Jensen, as I said, it's a really well-written package. I think it's very memory efficient. In its background, as far as I know, there is a lot of C implementation going on. So I'm very thankful that this package is presented by others because, as I said, it's really, really well written, and I highly recommend to you to check it out for yourself. Also, if you have some spare money left, I think they are also very happy about maybe some minor donations on their homepage. Nevertheless, if you use it here, we also, for instance, can check out some word models, Word2Vec models, for instance, that are already pre-trained. And here there's a big one. It's trained on the Google News corpus. If you click on it, you can read about it for yourself. But that is not really an actual model that has been trained on a large amount of examples. Its embedding dimension is 300. And here, for instance, if we execute it for the first time, it's take a while to download them. But what you can do is you can determine the similarity. So for instance, here positive means which are the most similar words to the words crisis. And as you can see here, it really makes sense, right? Crisis, turmoil, recession, downturn, also subprime mortgage crisis. Very interesting to me that this is showing up. But here you kind of also, if you have now learned how the model is trained, no big surprise, because in 2008 there has been the great financial crisis, which has been triggered by the subprime mortgage crisis and the downfall of the Lehman Brothers Bank. And this is why, for instance, crisis is also very related to subprime mortgage crisis. A quick word about the similarity. I think that I think in one of the form videos, maybe I also explained this. I'm not 100% sure. But as I said, you can calculate similarity between vectors by different metrics. Here, the common one is cosine similarity. If you are kind of used to how vectors are used in school or explained in school, very often they are used like in those 2 dimensions, and then you can take a look of the angle between the 2 vectors. And a cosine similarity is high if the angle between 2 vectors is small. A Euclidean distance, for instance, is high if the actual distance between the vectors is small. So, but nevertheless, I would say for the moment, just accept that there are metrics that as input 2 vectors and output 1 number. And here in that case, technically, here cosine similarity is used in the background. It's between -1 and 1, and the higher it is, the more similar the vectors are. Here, to get an idea what's the actual range of word vectors, for instance, what I'm doing here is I randomly collect 10,000 vectors out of the dictionary, which is by far more large. And then for every pairwise combination, I determine the cosine similarity. And then you can see what the actual range of similarities is here, just that you know here. Also, another aspect, maybe more to add to the practical considerations, you can see here that why do we have subprime mortgage crisis to be identified as a unique word? There's also the concept of n-grams, and n-gram would mean that we also include in the training every possible, for instance, if we talk about bigrams, 2 word combination existing in the corpus. So that means we would include 2 determined word, and similarities. Obviously, that really blows up the amount of all the numbers. So another suggestion by the authors of the Word2Vec model is to use a phrases identification. So before you actually train the Word2Vec model, you take a look at the relationship. How many times do 2 words appear together, and compare them to how many times do they appear uniquely. And like intuitively, if you observe certain, for instance, 2 words combinations more often than by the same 2 words by themselves alone, then you may consider them to treat those 2 words as a unique term. So New York, for instance, is a very good example here. All right, then with respect to the calculation, and I think this is also one of the most spectacular things in the original paper, is that now calculating with words becomes a really meaningful thing. So for instance, and this is like the go-to example in this model. So if we have the relationship of women to men should be somewhat equally or very similar to of the relationship to queen and king, right? So if we take a look at this here, and now if we know that those are vectors, and we know that we can subtract or add vectors, and we say, let's treat this as an equal sign for a second, we can reformulate this. So that means we can add king on both sides. So we would have women minus man plus king. And if that is equal, then that should be equal to the vector of queen, or at least approximately like equal or close to that. And this is exactly what is happening with Word2Vec word vectors. So this can be done manually, but here also with the chansim similar by vector, or the most similar functions, you can calculate this here, as you can see in the cells if you're interested. And this is exactly what you get here. So if you calculate women minus man plus king, the vectors, and now take a look at the resulting vector, which is the most similar I can find, it is king here, right? So, it is king. Yeah, it is king, obviously, and then queen. And so here, again, it's done with the normalized vectors. Now it works a little better. I don't know why a king is here showing up, to be honest. So let's just, let's ignore that. Sorry, I mean, kind of that's a relict here, some artifact, but you can calculate this with the most similar function as well. So positive means is the vectors that you would add up. So here, women plus king. Negative is then the vector that you would subtract. So that is man here. And here now it works, and the difference here is that this is using the normalized vectors, which is better and numerically more stable here. So, but that's the point here. So the real spectacular thing is that we calculate with the vectors, and it's kind of like the vectors behave as the words behave in our natural language. Like they have very similar relationships. That is what is the spectacular thing here, okay? All right, then what further can you do? So we have similarity. With this, as I said, with this calculation, this opens up to so much more, right? So I don't know, for instance, you can, I don't know if I have this here. Yeah, like you can do stuff like this. Let's go first here. So you can say I have 3 words that are supposed to describe a topic. So environmental, social, and governance. Those are like from the financial area and are related to non-financial factors. And if you take a look, what is most similar to this vector, so if we present this to that, what is called the keyed vectors in GenSim, it actually, what it does in the background is it averages, as far as I know, the vectors of those 3 words. And it also would be equivalent if you sum them up. It's taking a look what is then the most similar vector to those vectors here. And if you take a look here, this is to me really also impressive, because it kind of completely makes sense, right? You define the topic which is about environmental, social, and governance, and then you have ecological, but we also have sustainability, but we also have governance, for instance, and so things that are related to any of those words here. And this comes again from the fact that we can use just vector calculus here and build a meaningful vector by averaging the vectors of certain words here. Last but not least, what you also can do, even though there will be a model later on which is maybe more reasonable for this, you could also create now numerical representations of sentences. So if we take a look at those 4 sentences, what you can do for every sentence, you can create a sentence embeddings by collecting the embeddings of the words and then, for instance, summing them up or averaging them. So here I'm averaging them. And again, the result will be meaningful vectors for sentences, in the sense that the sentences that are closely related to each other by their meaning are also more similar when you take a look at the vector representations. And here the first 2 sentences, they are about ice cream and the taste of ice cream. And the 3rd, the 4th sentence are about the capitals of Paris and Germany. And as you can see, sentence 1 and 2, they are very similar to each other, by far more similar than to sentence 3 and 4. But here 3 and 4, which are both about the capital of the countries here, they are again similar to each other. Okay, so that also works. And that is, for instance, something which might be very useful if you want to do something else. So if you have, for instance, text information and need to predict something out of the text information, then you can now transform in that way a text into a numerical representation, which is then going to be the input for a machine learning model to be trained for, solving a prediction task or something like this. All right. I think there are many more things, but I think at this point that is enough. You can also visualize the vectors, but I think that needs to be done with some caution. So let's not open this box anymore here. And as I said, it's really about getting comfortable with the idea that words or documents are represented by numbers, by meaningful numbers, and in an alternative way than just counting the frequencies of the words. Okay, so that is what this video is supposed to be about, and also the last one. And then in the next one, we're quickly going to take a look, if you're interested, just as a demonstrational purpose, how you could use GenSim, as Word2Vec implementation, to train your own Word2Vec model. And for instance, why you would like to do this, maybe as a last thing, while these Google vectors are trained obviously on a very common language, in the financial area, for instance, it always has been showing that using domain-specific language is more promising for solving certain tasks here. So that is why, for instance, what also I'm doing sometimes, I collect financial text documents, a large amount, that's my corpus, and train the Word2Vec model, and then better use, for instance, those embeddings if I am more, if my goal is to tackle a task that is related to the financial domain, using, for instance, financial documents, and let's say, for instance, also making predictions regarding stock market reactions, something like this. Okay, so that is why you want to use domain-specific models for yourself. Besides that, if you don't, then I would say go with the models that have been trained here, because they have been trained using large resources, sophisticated people doing this large amount of text, and then they should be usually better than your own trained model on a general, like using more like the general language of daily life. However, still, as a task or to learn more about it, it is always also a good idea to do that for yourself. Let's do this in the next video, and then see you there. Goodbye.